All right. So here we have a Raleigh criteria example. Guess I'll say hi. Hi, you guys. Hope it's going well today. And that you're cranking through these and figuring some stuff out. This one actually throws us back and has us review something that we've already learned, but it's a pretty straightforward question and good to remind ourselves how to do those problems as well. So let's take a look. So it's Raleigh criteria question. We have two oranges that are 54 centimeters apart from each other, which is pretty far apart. And then we're going to actually look at it with a little telescope and be curious about, well, how far away technically could we get to be able to resolve those two oranges as separate things. And so the Raleigh criteria equation here is what we would use. But we need to know the wavelength. But since they're oranges, we will estimate that the wavelength coming off of them is orange. So that's the 630 nanometers, which we'll have to turn it into meters. The 1.22 is because we are using a telescope, so it has a diameter. It's not a slit opening, but is instead a circular opening. And we need the diameter to be in meters here. B is the diameter of that circular opening. So we'll take the 24 and turn it into meters, and that'll be easy plug and chug. And we'll get radians. Radians are technically unitless, which if you're wondering well, this is meters over meters, all the units have gone away. So don't worry about that because radians are technically just a ratio, right? And you know that from the definition of a unit circle and what radians are. It's like the arc length along a unit circle, so it could be of any units because it's that ratio. In any case, that's going to be a pretty small number. If you think about it, you're trying to look at two oranges that are, and you're looking through a telescope at them. So the angle that's formed between wherever you are looking at these two oranges is going to be a very, very small angle. So we can use simple approximations to that and use that angle with an arc tangent and the fact that they are 54 centimeters apart from each other, using this angle in radians and approximate that with the tangent of the angle in radians, and it'll be the same thing because at very small angles, the radians of the angle themselves is equal to the sine of the angle, which is equal to the tan of the angle. They're all slightly different technically, but they're all so close to each other that we use those small angle approximations. So then it'll be really easy to figure out how far away it is using this as the angle. And assuming, and that's a big assumption, that with our telescope and our eyes, we have this perfect Raleigh criteria situation going on, which is obviously not valid because there can be effects in the air itself because we're assuming we're not out in outer space. There's going to be atmospheric distortions that are created. Also, the optics of the telescope, unless you spend a lot of money, aren't going to get you close to this. And even if you do spend a lot of money, aren't going to get you to this. So your eyeballs are the other place where your eyeballs have a certain number of cells, on your retina, and you have distortions in your eyeball because you don't have perfect vision. And so there's no way we're going to get this actual distance amount. But anyway, this is sort of the theoretical maximum distance, and the real distance won't be so far for us to be able to tell the two oranges. So pretty plug and chug and straightforward question. I guess I can just verify that we get what we do here. So the lambda, we've got to put 10 to the negative ninth because it's nanometers. Right here we had to turn the 24 into meters. So we get our radians, and if that's an answer, we would display this with two sig figs. But in subsequent calculations, we'd use the unrounded one, as you can see here. Here we're using the actual angle between the oranges to be the arc tangent, but we're not bothering to take an arc tangent. We're just taking x, the distance between the two oranges, divided by d, which is how far away they are. Solve for d, so we get x over theta, which we have theta here, so we just plug it in. And we get about 170 kilometers, which would mean it'd have to be up on a mountain or something and you're far away and the light would be just right and you're looking through your telescope and it'd have to be a very expensive telescope. But there you go. That's the Raleigh criteria. Here I said turbulence in the air, perfect optics means there's no way we would get to this number. As you saw, hopefully, when you're doing your angular resolution activity that we did earlier. So hopefully this just verifies some of that, those ideas, and is a nice little practice problem to give you some confidence, hopefully. And there we go. We'll do the next one here soon.